Section 3.3, Arc Length and Curvature. In this section, we talk about how to determine the length of a portion of a vector function curve, and then we also talk about how to describe the curviness of these vector function curves. Arc length for a plane curve. Remember, that's a curve that's stuck in 2 dimensions. For a plane curve defined parametrically by, let's say, maybe the functions f of t for the x and g of t for the y. If we wanted to define the length of a curve between the parameter a and b, we would use the integral of the square root of the sum of the squares of the first derivatives of our 2 parametric equations. A vector function defines a plane curve very similarly. So that plane curve that's defined by f of t and g of t, we can take those 2 parametric equations and plug them into a vector function, and the vector function can describe that exact same plane curve. And so naturally, if we wanted to calculate the length of that plane curve between the parameters t equals a and t equals b, we'd use the same integral. To give ourselves a bit of a visual for this expression, let's take a look at the graph on the right side of the screen. I have a 2D plane curve that you could say is defined either parametrically or by a vector function. Either way, you would get the same graph. And I have a pair of orange points plotted at the top of this curve, and those orange points correspond to some parameter value. We'll call them t equals a and t equals b. And so calculating the arc length between those parameters, t equals a and t equals b, it's finding out how long this portion of the curve is between the 2 orange points. And similarly, between the 2 green points, these are corresponding to different values of t, some other a and b pair, and we're calculating the length between those 2 green points. Now, a curve that's defined in 3D would have 3 component functions, something like f in the I hat component, g in the j hat component, h in the k hat component, and we can still ask the question, how long is the arc length of the curve defined by that vector function between the parameters t equals a and t equals b? And the formula for arc length is very similar here. It does require each of the component functions' derivatives to be squared, added together, square rooted, and then integrated between the 2 parameters a and b. But notice that there's something familiar happening here. For the vector function r, notice that the first derivative of r prime, is the derivative of each of the component functions. And if I were to then take the magnitude of that first derivative, I would take each of those derivatives, f prime, g prime, h prime, I would square them, add them up, and square root them. And that looks like exactly what we have inside of that arc length formula. And so we can replace the notation here and simplify ourselves by writing that s, the arc length of a curve, is equal to an integral between the parameter values t equals a, t equals b, where we're integrating the magnitude of the first derivative of our vector function. Let's go ahead and try calculating one. So I have a 2D curve here, and I'm going to use this formula that we just talked about at the bottom of the screen. I'm calculating it between t equals 1 and t equals 5, so I'll use 1 for a, 5 for b. And now I need to find the derivative of each of my component functions. So let's call the function in front of I hat f, and we'll call the function in front of j hat g. So that would make r prime of t equal to 3 I hat plus 4 j hat. And then to finish our formula, I need to take the magnitude of that first derivative. Magnitude says take each component, square it, add it together, square root it. We get 9 plus 16, which is equal to root 25, or which is equal to 5. Our formula says that we integrate the magnitude of the first derivative of our vector function. We found the magnitude of our first derivative of our vector function is 5. So we're going to integrate 5 with respect to t. Oh, I forgot my equals sign. This should say s equals this integral. And now we can integrate. The integral of 5 with respect to t looks like 5t, and we integrate from 1 to 5, just like we learned in Calc 1 using the fundamental theorem of calculus. We'll evaluate our endpoints, 5 times 5 minus 5 times 1, to get an arc length of 15. So this vector function, r of t, between the parameters 1 and 5, the length of the curve is 15 units long. And if we wanted to graph that, we could see the vector function is plotted in white. The parameter values t equals 1 and t equals 5 are points on the curve. And then I've shaded in the portion of the curve between those points in light blue. That is the portion of the curve that we just calculated the length of. So that was the thing that's exactly 15 units long. Let's try another practice problem, this time for a curve that's defined by a 3D vector. I've got it graphed over here on the right side of the screen. The vector function is mapped out in white, and then between the parameters that we're integrating over, we have t equals 0 at this point here, and then we have t equals 2 pi at this point here. And we're trying to find the arc length of this portion of the curve that's shaded in blue. So to do that, we'll use the formula for arc length that we just discussed, which requires us to find the derivative of our vector function. Looking at the first component of our vector function, I do see a product of two functions of t, which means I do need a product rule here. The derivative of that first function, t, is 1, and then multiply that by cosine. Then I add to that the first function, t, times the derivative of cosine, which is negative sine. In the second component, I also have another product of two functions of t, so I'll need a product rule here too. And in the last component, I don't need a product rule. The derivative of 2t is just 2. Next, we need to take the magnitude of that first derivative. Take each of our components, square them, and add them up. And then after we've added all of those up, we square root them. Now at first glance, this looks pretty gnarly. We've got a binomial squared, another binomial squared. We need to multiply those out to see if we can simplify any of this. So let's go for it. Cosine t minus t sine t, when we square that, that uses the pattern of a perfect square binomial. So the first term squared minus 2 times the first term times the second term, and then plus the last term squared. That would be t squared sine squared t. That second term, the second binomial squared, follows that same pattern, so I'm going to just write that right below. It'll fit over here. Multiplying it out using the same pattern. And then we have our 2 squared at the end, which is 4. And don't forget, all of this is inside of a square root. It's a long square root. Now here's the part where it looks intimidating, but we can see some things that will clean up for us. For example, I have a cosine squared t plus a sine squared t. I know that those things together add up to be 1. I also have a t squared sine t and a t squared cosine squared t. If I factored off the t squared, I would have sine squared plus cosine squared again. I'm going to write those terms side by side so that you can see exactly what I'm saying. And then I'll bring down the rest of the terms. And remembering all of this is nestled inside of a very large square root. Now arranging the terms like this, I can see that cosine squared plus sine squared equals 1, and then I have a t squared times 1 as well. Also, I have a negative 2 cosine t times t sine t, plus a 2 sine t times t cosine t. Those two terms have all the same factors, but they are opposite signs, so they add together to be 0. So this square root function actually simplifies quite nicely. I have a 1 plus a 4, so that's 5, and then I have plus t squared. So this is the magnitude of the first derivative, the thing that we have to integrate. So let's set up our arc length integral. Between the parameters t equals 0 and t equals 2 pi, we're integrating the square root of 5 plus t squared dt. Now just to take a second and pause, we aren't integrating a vector function here. We're integrating the magnitude of the derivative of a vector function, but when we calculated the magnitude, we took a vector, r prime, and turned it into a scalar function of t. So the square root of 5 plus t squared, that's a scalar function of t. So this is really like a Calc 1 integral, not that new. Something that is a little bit frustrating though is this is not the easiest integral to evaluate. So if it's been a while since you've done integrals like this, it would be great for you to go back and review those. I'm going to go ahead and use the table integration formula for an integral that follows the form of the square root of u squared plus a squared, where u is the variable. So if I was trying to evaluate that integral, the table tells me it would look like u over 2 times the square root of u squared plus a squared plus a squared over 2 times the ln of u plus the square root of u squared plus a squared, all in absolute value, plus some constant if I were doing an indefinite integral. So applying this to the integral that we're looking at, instead of u, we're working with t, and instead of an a squared, we're working with 5. So that would mean we're using t in place of u, we're using 5 in place of a squared. So anywhere we see a u, we would replace it with t, and anywhere we see an a squared, we would replace that with 5. So for our integral, that would look like t over 2 square root t squared plus 5 over 2 ln, whoops, kept a u there, that should be a t plus square root t squared plus 5. And I don't need the plus c because I'm going to evaluate this integral between 0 and 2 pi. Plugging in our bounds, 2 pi first for t, and then subtracting off this antiderivative evaluated at 0. It's a lot of calculator scratch work, and it will result in the value of approximately 25.343. Now we don't have the context of this problem, so I can't tell you if that's about 25 inches, 25 centimeters, 25 millimeters. We just know it's 25 units of length, so I'll write that it's approximately 25.343 units. And that represents the length of the curve that we were looking for between the parameter values t equals 0 and t equals 2 pi. There's not a whole lot of new concepts going on here. We already know how to find the derivative of a vector function. We already know how to find the magnitude of a vector function. We also know how to integrate a scalar function. We learned that in Calc 1. So the only really new concept here is that we're using this integral that's equal to s to calculate arc length for a vector function. We know that arc length is calculated by this integral equal to s. But if we were to adjust the bounds just a little bit, instead of integrating from values t equals a to t equals b, maybe we pick a starting point at a and we allow the upper bound t to be a parameter that moves. This way we can create a function that calculates arc length starting from that specific point A, but going as far down the parameter as we'd like. I have a little animation to show you what I mean. I have a vector curve plotted here in white, and I have a starting point plotted in blue. And if I were to show you that I'm calculating arc length with t allowed to move forward, then our arc length can go as far up along that curve as we want. This is a useful idea because we can reparameterize our function using this s of t function that we just created. Recall that when we first learned about vector-valued functions, we said that you can reparameterize the curve, but it won't change the curve's visual appearance in space. That means we can find this s of t function, and we can use it to then plug back into our VVF so that now the parameter s is related to exactly how long the curve is starting from that initial point. So we can use s of t to reparameterize the function so that our parameter is related to arc length. Most of the time, the parameter t is completely unrelated to arc length. And again, most of the time still, we can't even find this s of t function. I'll show you what the dilemma is. Let's try a problem here. R of t is equal to 3 cosine t, 3 sine t. That is the curve that you see in blue on the screen. If I calculate the derivative, I get negative 3 sine t for the x component and 3 cosine t for the y component. So then the magnitude of that derivative would be negative 3 sine t squared plus 3 cosine t squared, all of that square rooted. That's actually the same as the square root of 9 times sine squared t plus cosine squared t. If you don't see that immediately, I would suggest you pause and go ahead and multiply out your squares and combine like terms. And then you'll see that we're really looking at the square root of 9 times 1, which is the same as the square root of 9, which is just 3. So here we're integrating from a starting point of 0 to maybe the parameter t of the magnitude of our first derivative, so that's the 3 that we just found. We're integrating with respect to, we have to be careful here. We can't integrate with respect to t if t is in our upper bound. So I'm going to use a dummy variable here. I'm going to use u. And I'm going to let this integral be my s of t function, the function that relates the arc length parameter s to the original parameter t. So then we apply the integral, 3 integrated with respect to u becomes 3u, and then we evaluate that from 0 to t. That looks like 3t minus 3 times 0, which is just 3t. So this arc length function, s of t, is equal to 3 times t. That's the relationship that says s is equal to 3t. T is our original parameter. With no relation to arc length, s is the arc length parameter. I can replace t with s as long as I solve this expression for t, and then I can redefine my function as a function of s. So solving this for t requires that equation to be invertible. Sometimes when you calculate this s of t function, you will not get an invertible function, meaning you cannot solve this equation for t. It's just not reasonable. So you would be at a wall there. In this case, we would just divide both sides by 3. So we'd get s over 3 is equal to t, which means I can go back to my original vector function, and everywhere there was a t, I can replace it with s over 3. Now, technically, I wouldn't do that in the function notation for r of t. I just do it in the function definition. So I would rewrite this function as r of s to really highlight the fact that the parameter s is directly related to arc length. And then the vector function would look like 3 cosine of s over 3, and then 3 sine of s over 3. The points that are generated for this version of the vector function between increasing values of s, maybe s equals 0 to s equals 1, that's exactly 1 unit along the function. So if I plot a couple of these points, I see r of t starting here at the origin, and then if I let t increase by 1 and continue to increase, I'll see these new points along the function. Now those orange points are not 1 unit apart from each other. These green points are. Now I've only chosen to plot a few points so that I can really show you that the arc length parameter s does generate points that are exactly 1 unit apart from each other, whereas the original parameter t is generating arc lengths that might not be 1 unit long. In fact, the orange points might not even be perfectly spaced apart. Sometimes the orange points could be closer together, sometimes the orange points could be farther apart, even on the same curve, whereas the green points are always exactly the same distance apart from each other because the green points are defined using that arc length parameter. This r of s function at the bottom of the screen, this is what we call the reparameterized vector function. We've reparameterized the function so that now it is a function of s instead of t, but the function still produces all the same points at the end of the day. It just produces them in a more orderly fashion. Let's try another arc length parameter problem, where we're looking this time at a 3D vector function, r of t. So again, we're going to start by finding that s of t function using this integral. So we need r prime, which would look like negative 3 sine t I hat plus 3 cosine t j hat plus k hat. So that's just the first derivative of our vector function r. Next, we need to take the magnitude of that. That's going to look like 9 sine squared t plus 9 cosine squared t plus 1 squared. The 9 sine squared plus 9 cosine squared simplifies to just be 9, and then I have 9 plus 1, so the magnitude of r prime is the square root of 10. And that is what I will use to create the s of t function. So we will integrate starting from 0 because our problem says that t is greater than or equal to 0. So our bottom bound on the integral is 0. The top bound will be t. Then we're going to integrate the magnitude of the first derivative function, which is the square root of 10 as we calculated it. And then we're integrating with respect to a dummy variable u. Remember, we can't put t here in the integral because t is on the upper bound. So we're just going to rename our variable inside of the integral. The square root of 10 becomes the square root of 10 times u, which we then evaluate between 0 and t. And that simplifies to be root 10 times t. So in this case, the arc length parameter function s of t looks like t times root 10. And it might help to, instead of writing s of t, just write s, so that we can see the relationship between the variables s and t, or sorry, parameters s and t. And we want to invert this function so that it now looks like a t equals expression rather than s equals. And we can simply do that by dividing by root 10. So solving this for t, we get t is equal to s over root 10, which means we can go back and reparameterize our function r of t to be this same curve, but parameterized using arc length s, where the t in our original vector function is replaced with s over root 10. I have the curve plotted here in blue, and I think I made an animation for us to watch. I did. So I have the original parameter t generating points along the curve. And then I've reparameterized the function. So now we have the vector function of the arc length parameter s, and we can see the points generated by this reparameterized function are exactly 1 unit apart from each other. Now again, this is useful, we'll see later on, but it's not always possible. There are many functions out there that we cannot reparameterize. So you might wonder, why would we bother talking about this? Well, because we could then use theory about general functions to come up with expressions for other uses. You'll see what I mean in just a moment.